Hello everyone, I'm Grzegorz Dudek from Częstochowa University of Technology, Poland. Today I'll present the results of my recent research on data-driven learning of feedforward neural networks with different activation functions. After introduction, I'll show the framework of the data-driven learning. Then I'll present data-driven learning with different types of activation functions. In the simulation study, I compare the fitting properties of this method with different activation functions. And finally, I'll conclude the work. Typically, feedforward neural network learns using gradient descent methods, which suffer from many drawbacks, which make the learning process ineffective and time-consuming. Randomized learning was proposed as an alternative to gradient-based learning. In this approach, the parameters of the hidden nodes are selected randomly and stayed fixed. The optimization problem becomes convex and can be solved by a standard linear least squares method. This leads to very fast training, good generalization properties, and ease of implementation. The main problem in randomized learning is how to select the random parameters. Recently, several methods for generating hidden node parameters were proposed, including data-driven method. This work contributes to the development of the data-driven method by introducing different activation functions. In this study, we consider a single hidden layer feedforward neural network with single output. Weights A and biases B are generated using data-driven method. We have M hidden nodes and activation functions H. Here sigmoids, but we will use different functions. And output weights beta. The network expresses function phi. The output weights beta are determined using the Moore-Penrose generalized inverse of matrix H, which is the hidden layer's output matrix. The algorithm of data-driven method is as follows. In the first step, we select randomly training point x asterisk and its k nearest neighbors. This is set C. This set is shown as red points in the figure. Then we introduce the sigmoid S into the input space. It is set in such a way that one of its inflection points, P, is in x asterisk. The sigmoid value at the inflection point is 0.5, so we get this equation, from which we obtain the bias B. Note that the bias depends on the weights and randomly select the training point. In the next step, we fit the hyperplane T to the target function in the neighborhood C. Assuming that sigmoid S is tangent to this hyperplane, we obtain the weights deciding on the sigmoid slopes. Resulting sigmoid reflects the target function slopes around the point x asterisk. Similarly, we set other m sigmoids. Now we will derive formulas for the hidden node parameters for different activation functions. First, bipolar sigmoid, defined by this equation. In comparison to unipolar sigmoid, the only difference is the output scope, which is from -1 to 1. Data-driven method places the sigmoid in the input space in such a way that one of its inflection points is in the randomly selected training point x asterisk. The bipolar sigmoid value at the inflection points is 0. So, equating the sigmoid equation to 0, we get the formula for B, which is the same as for the unipolar sigmoid. To find weights, we equate the partial derivatives of sigmoid in x asterisk to the partial derivatives of hyperplane T, which is just the coefficient A prime. From this equation, taking into account that the sigmoid value in x asterisk is 0, we obtain the equations for weights. Note that the sigmoid slope in the inflection point is the same as the line t slope, which approximates the target function slope around point x asterisk. In the case of sine activation function, a data-driven method places it in the input space in such a way that it has one of its inflection point in randomly selected training point x asterisk. The sine value in the inflection points is 0, so equating the sine equation to 0, we get the formula for b, the same as earlier for sigmoids. To find weights, we equate the partial derivatives of sine function in x asterisk to the partial derivatives of hyperplane t. From this equation, taking into account that the sine value in x asterisk is 0, we obtain the equations for weights. As you can see, the weights are the hyperplane t coefficients. Now saturating linear unipolar function. This function is placed in the input space in such a way that it has a value of 0.5 in x asterisk. This is analogous to unipolar sigmoid, to which this function has a similar shape. Assuming that the function value in x asterisk is 0.5, we obtain the formula for bias. We assume that the middle segment of this function has the same slopes as hyperplane t, so the weights are the same as hyperplane coefficients. Saturating linear bipolar function. Analogous actions lead to such formulas for weights and biases. Results for ReLu. In this case, we assume that the half hyperplane of which ReLu is composed coincides with hyperplane T. And results for softplus. To compare the fitting properties of the data-driven method with different activation functions, we report the experimental results over several regression problems, including an approximation of extremely nonlinear target functions. Last three functions are multivariate ones. We consider them with 2, 5, and 10 arguments. Look at the results of TF1 fitting. Network included 30 hidden nodes, and the neighborhood size was 2. The activation functions distributed by DDM in the input interval from 0 to 1, shown by the gray field, are shown in the lower panels. As you can see from this figure, the slopes of the activation functions reflect the target function slopes. The best fitting results were achieved for both sigmoid activation functions. Sine can't cope with a target function with variable intensity of fluctuations. Neither ReLu, which yielded the highest error, nor the saturating linear functions are not able to fit smoothly. softplus improves on the ReLu fitting results by offering a smooth approximation. Fitting results for TF2. Also in this case, sigmoid activation functions provided the best fitting. These figures show the fitting errors for different number of hidden nodes for TF1 and TF2. As can be seen, the sigmoid activation functions outperformed all the others. Slightly worse results were achieved for softplus, while the highest error was observed for ReLu. Fitting errors depending on the number of hidden nodes for other target functions. For n equals 2, the sigmoids yielded the best results. For n equals 5 or 10, results for all activation functions were comparable. This could be explained by the change in the target function landscape, which flattens with the increasing number of dimensions. For flat target functions, the activation function's shape is not as important as in the case of target functions with strong fluctuations. Detailed results, root mean square errors for the maximal number of neurons. The lowest errors, those that are at least 5% lower than the others, are marked in bold. No results for softplus for multivariate target functions because it caused numerical problems due to its rapid growth. Conclusions. The data-driven feedforward neural network learning described in this study is an alternative to both standard gradient-based learning and randomized learning. It allows us to bypass the tedious iterative process of tuning weights based on gradients. In the proposed approach, the parameters of hidden nodes are calculated based on the local properties of the target function, and consequently the activation functions reflect the target function landscape. Data-driven method finds the network parameters quickly without repeatedly presenting the training set. Network performance strongly depends on activation function shape. In this work, using a data-driven approach, we derived equations for the hidden node parameters for different activation functions. As our experimental study has shown, the best performance in smoothing highly nonlinear target functions was achieved by the sigmoid activation functions. They were able to fit to the target function fluctuations. In contrast, ReLu activation function, which is very popular in deep learning, fared very poorly in fluctuation modeling due to its piecewise linear nature. Its smooth counterpart, softplus, produced much better results but suffered from numerical problems related to its rapid growth. Thank you very much for your attention.